Okay, it seems that if we have complex systems, second order, third order system, fourth order systems, getting these values one by one is not easy, right? And as we increase that, so we need to plot that. In this case, it's okay. We have two poles. We can still calculate, and then we get this. Okay, this is the one that we want. This is the one that we know that whatever k values that we increase in these systems, whatever k the value, so the poles will move to these directions. They don't go to the right, so that cause the system unstable. So in this case, we can see that clearly the systems is moving towards the left as k increases, right? So the system is all the time stable. Remember in RH criterions, we define that what is the k value that cause the system to be unstable. That is when the system actually, the roots of the closed loop system move to the right side of the S-plane, then the system become unstable. In this case, we see that whatever k values, even you put the infinity values, the system will actually remain stable. All right, so this is the purpose of having this. We are not actually interested to see the exact point here. We want to see where the system is going. Is it going to this direction? Is it going to this direction or this direction? So that is important to determine the stability. All right, okay, let's move on. This is not clear. Okay, never mind. I think this idea is just to verify whether this point A is belong, this point A here actually be locates along this root locus or not, just to check, right? If they are not part of the root locus, this point does not actually fulfill the g of s equal to -1. That's the thing. But actually, this is not really important. It's just to verify that any point along this line should fulfill these criteria. That's important, right? If in this case, if we pick any point, arbitrary point here, we test it here, so it does not satisfy this. So that means that point is not on the root locus. Okay. Okay. In this example, we have poles, one zeros for the closed loop, for the open loop systems. So first we need to plot the zero and poles on the S-planes. So s equal to -2 for poles, s equal to -3 for zeros. Then you can plot here. This is poles and then 0. So the root locus, if we have 2, okay, the root locus actually, as you increase the k in closed loop, actually it is moving towards the 0 as k increases, right? Or k increase to infinity. So this is the root locus. So you know that the system will remain stable for whatever k values. You can verify that. Okay. Okay, now because the calculating the roots and the poles, the roots and the zeros for a closed loop system is very troublesome. So we need to use the rules, all right? So there are a few rules to follow in order for us to plot the root locus, right? The main rules are, first, you need to see these two rules first, okay? The root locus must be symmetrical about the real axis and must not crossing or overlapping each other, okay? That's first rule. Now we'll have a look later. For system with infinite zeros, incomplete pole zero pair, the locus need asymptote line, okay? So that means the directions where it's going to go. Okay, and then the additional root locus parameter. So we have angle of departure, we have angle of arrival, we have a breakaway point and break-in points. We have to calculate j omega crossing points, and then we need to determine the stability limits. In this case, we can use the average array. Okay, okay. Let's see what does it mean. Okay, now based on these rules, we can draw the rule locus. Okay, okay. Now we need to, what does it, what is the meaning of this? Okay, so what is the breakaway point, break-in point, and so on? Okay, you see that we have 10 criteria or 10 um, item to verify here. The first one, number of branches. We need to determine how many branches, right? That's the system has. The branch means this consider for one branch, second, third, and fourth, right? Okay, number of branch and at finite zeros. If we have a zeros, so this the closed loop poles will actually find the zero. This one will find this zero. This one will find 1 0 here. This one will find another 0 at infinity. Okay, so number of branch um, and at finite zeros are 3. 1, 2, 3. That determines by the number of 0 we have in the systems. If we have a 3 zeros, then this becomes 3. Number of branches and at infinite 0, there's a 1 right here, because this one is going to somewhere that's there's no 0, we can see from here. So infinite 0, this one. Do we need asymptote? Yes, because if we have infinite zeros, we need to have asymptote, because we don't know where it's going. Okay, that's breakaway point is the point where this line will break away from the real. That's the breakaway point. You go check and see this one. Breakaway point is a point where the root locus split out from real axis pole to imaginary. So this is breakaway point. There are two breakaway, and this is break in. Okay, okay. Remember, as we increase key values, the closed loop poles actually moving from open loop poles from here towards finding the directions of the zero, open loop zero. So that means the poles is always moving towards zeros. Okay, so breakaway point is here. That means it's actually, this one is moving this direction, this one is moving to this direction as k increase, this one is moving this directions, and then it will break away because this is a breakaway point. Okay, this one is a break in point because it's break in. Okay, point from these poles to 0 here, so it is actually break into the um, uh, real axis. So we have also angle of departure. So as we have a breakaway point, we have angle of departure right here. No, this is no, sorry, angle of departure. Departure must come from poles, right? Where's the angle actually? Where's the locus actually going to this 0? What in at what angle? So there is the uh, departure angle. This is arrival angle, right? Because this is going to 0, so we call it arrival. Okay, imaginary axis crossing. Okay, if for some system we don't see not all these parameters are available for all systems. Some systems like this one does not have any angle of departure, angle of arrival, don't have that. And then there's no J omega crossing. So this one has J omega crossing, yes, yeah, here. System stability, so we need to determine the system stability. What is a K value that the systems before the root locus actually going to this direction? So what is the K value at J omega crossing is critical then, right? So to determine the stability of the system. Okay, now as you can see there, if we have a different systems here, example, right? So we have a two zeros, two poles. That means they are complete pair. There's two poles, two zeros. We can see that these poles will move towards 0. These poles move towards 0. Okay. So any systems that has a complete pair, let's say T of S, S plus 3, S plus 10, S plus 20. Okay. So this one, we know that it has a complete it has a complete pair. So that means these poles will find one of the zeros here. So this is minus 10, minus 12, zeros, minus 3, 0. Okay. We know that somehow this one will find this 0 is going to this direction, right? But the rule says here, in this case it's okay because it doesn't violate the rule. The rule says the root locus must be symmetrical about the real axis and must not crossing overlap each other. That means as this one is going to this direction, this one cannot overlap, right? Okay. So and then it must be symmetrical. So we need to find a way how to make it symmetrical, right? So we need to check a few things here. They are completes. That means they have both. They have two poles and two zeros. Okay. Number of branches depends on the number of zeros, right? Number of poles. So there will be two branches here. So from here we can see that the item number 1, number of branches, we have 2, right? See number of branches. Number of branches is count based on number of poles. Number of branch at infinite 0. Number 2, 0, because there's no infinite 0, right? There's a complete pair. So unless we have one system like that, so that means we have 2 poles and 1 zeros. That means we have 1 number of branch and at infinite 0. No, sorry. Number 2 supposed to be 2. Number of branch and at finite 0, we have 2 finite zeros. Number 3 have zeros, right? There's no branch and at finite zeros. So do we need asymptotes? Asymptotes is number 4 because we don't know where it is going. We know the fact that this one is moving to this direction, but the rule number 2 say, rule number 1 say it cannot overlap. Okay, if we draw like this here, then this one is overlap each other. You cannot. All right. So we need to be, and then we need to be symmetrical about the x-axis. So if we do like this, is it symmetrical? No, it's not symmetrical. Symmetrical is a mirror, meaning that if you have one is going this direction, must be like this. If you have like this, maybe it's like this. So it must be symmetrical, mirror about the x-axis. This one is not mirror. So Even you draw like this, it's not mirror, right? So what we're going to do is, in this case, we need to find the asymptote. Okay, this is the formula of asymptotes. Here, okay. The number of finite zeros, okay, minus the total of minus 0 minus the total of finite zeros, finite poles, and then divide by finite poles minus finite zeros. Okay, you get this, all right? So in this case, we have need to find this a equal to um, the finite poles 10, 20, right? So minus 10 minus 20 minus the summations of zeros, 0 and minus 3 divided by, this is number, so how many poles, number of finite poles, 2, 1, 2, right? 2 minus 2, right? Two number of finite poles, so this one is minus 30 plus 3, this is 0, right? So that is the so in this case, if we have a complete pair, right, that part becomes 0. We can't determine the angle, and then instead um, it is the angle of because there's no, okay, remember, I forgot to mention for asymptotes. Okay, asymptote line, let me see. So we need to make sure that we have incomplete pair, then we have asymptotes. So if we have a complete, we don't have asymptote, right? So in this case, we have a complete pair, these two poles and two zeros. Then we don't have the asymptotes, okay? Okay, now, so we have no asymptotes here. Okay. And then breakaway point. Do we have a breakaway point? Because the breakaway points determines by if a point when the root locus merge into real axis imaginary, right? So in this case, there is a breakaway point. So that means we have to find somewhere breakaway point. Again, the breakaway point is not really important, but later we have to calculate that. Okay. So now looking at this, okay, minus 3, 0. Okay. Now to get a symmetrical uh, root locus is that we have to move this to this direction from here, maybe here, then from here it is moving to this direction, moving to this direction, right? So that's you see, very symmetrical. So this is the um, break in point. This is breakaway point. Okay, you can refer in the book how to calculate this, or you can use this formula. Okay, so the idea is that by looking at this transfer function, we can sketch this using rules, right? So from here we know that as k increases, the system will be still stable, right? You can verify this in the MATLAB by running rlocus command systems, right? Okay, first one you need to define what is the systems in the workspace, s squared plus 3s plus 2, and then you run rlocus system. Then you can see that how the MATLAB plots the system to verify answers. Okay, let's stop here first.